Hi guys, I'm few minutes late to the contest. I'm like 2 3 minutes late to the contest. Let me go and try to solve this contest. You're given an integer and you need to construct a permutation. A1 8 upon using integers from 1 to n such that the following condition is satisfied. A1 mod A2 greater than A2 mod A3 greater than up to so on. I think some simple sequence will work out. We have to just figure this out. Greater than or equals to, right? Can we always make them 1 somehow? Like if you have n here and n minus 1 here, then their modulus is 1, right? And then n minus 2 up to so on. Will that work out? Yeah, that works out, right? Finally, it will become 0. So decreasing sequence works out here. Look at the reminder. 1 0 1 1 0. That's what we want. Submitting it. So A has been done by me. So now let's read B. There are n chairs in a row, initially all unmarked. You're given a permutation P of length, and now you play a game. You visit each chair sequentially, starting from the first chair. At the ith chair, you can do the following. The ith chair is already marked, then you end the game immediately without sitting on it. Okay? Otherwise, you can choose to sit on the chair or skip and move to the next chair. If you choose to sit on the chair, then after standing up, you mark the pith chair and move to the next chair. If all the n chairs are visited, the game ends. Your task is to determine the maximum number of chairs that you can sit on. So we have a permutation and we have to find maximum number of chairs that we can sit on. Oh, I am not sharing my screen. That's what I was feeling, something is off. So you visit chairs sequentially starting from first chair. At the ith chair, you can do the following. If the it is already marked, you are out. Okay? Otherwise, you can choose to sit on the chair or skip it and move to the next chair. So if you mark something, you can never cross that because if you come there, it's gone. Otherwise, you can choose to sit on the chair or skip it and move to the next chair. If you choose to sit on the chair, then after standing up, you mark the ith chair. So if you sit on something, it will get marked over there and move to the next chair. So I think we can clearly say something, right? You can sit on it and then you can mark something. But if you sit on that, you must mark. So it's like very obvious, like very obviously you can say something here. Uh, so you're starting from one. Okay, let's say there is a point, there is a partition, there is a board, there is a border. Okay, after this, some get marked, and before this, you can sit on them. So let's say before this you have sit on some chairs, and after this they will get marked, and you cannot sit on the things after this. So they will be separated, right? Because some things will get marked because you sat on some things over this side. Because you can never touch the first marked one. Because if you touch the first marked one, you're done. So maybe can you brute force on this partition is one thing you can think of. If you're trying to brute force on this partition, what you have to do is you have to uh, you have to see things for which pi is greater than I, for which pi is greater than I and I less than, let's say you're partitioning that, let that be x. Okay, you want You want count of I such that I less than x and pi is greater than or equals to x. If you are brute forcing x, okay, so let's just try to go like this side. Let's just try to make increasing x. As you're increasing x, you will get more and more I. But for existing i's, pi, this will fail, and then you will remove that. So you can do this. You can do this in as by just maintaining a set or something. You can do this, right? So we are brute forcing that x here. I'll just maintain a set of pair, and so can we always brute force this? Because if you take something, one will be marked, right? Otherwise, zero will be the answer. You can always take one. So let's just keep int answer equals to 0, and for I equals to 1, I less than or equals to an I plus plus, you will insert this, okay? And then so you have inserted this p of I comma I. If pi is less than I, it's anyway good, because if you are coming here already, it's good. If pi is less than I, it's already good. So you won't add it if pi is less than I. Because if it is pi is less than or equals to I, you need not worry, because you stand up and then you're marking it and then you move to the next chair. You only have to worry if it's coming in the future. Okay? Else you will insert n plus 1 comma I, let's say, which is like which will never be removed. Okay? Which will never be removed. And then we have to remove everything that is less than I, because that is not achieved, that's not achievable till here, because for this x that's not achievable. If we touch that, it will be gone. Okay, while it's passing, but have I brute forced it right? Think of that. If pi is less than I, it doesn't matter, because you came here and then you're marking something behind. Okay, but if pi is greater than I, you have to remove such things whenever you are x, you're brute forcing x. And am I brute forcing x in the right way? Here what my assumption is, if something is less than or equals to I, see, I'm touching till I, I'm marking till I is my assumption. So if I'm able to sit on things till I, okay, what does that mean? If I'm able to sit things till I, if something is before that and if it is less than I, then you cannot reach that, you're removing such things. So this should be correct. I'm able to sit till I is my assumption here. I'm brute forcing on the point where I can sit. Okay, but maybe I'm making a mistake with respect to less than or equals to and less than. But if you have to think properly, if I think properly, marking I after leaving it is always good. If you're thinking how one I can fail you, if you think how one I can fail you, if it is occurring before, it can never fail you. Occurring less than or equals to, it can never fail you. It's occurring later, it can fail you. But if your x is less than or equals to that, then it cannot fail you. It will fail you once after you go from there. Then you're removing that. Then you're not sitting on that. So in that way, you're brute forcing it, right? I believe. See, I just don't want wrong answers. If I don't get wrong answers, I can perform well in the difficult problems easily. This is the easy version of the problem. The difference between the versions is that in this version, 1 less than or equals to n less than or equals to 2e5 and bi equals to ai for all the indices. Note that the solution for one version does not necessarily solve the other version. You can only hack if you solve all versions of this problem. You're given two arrays a and b of length, and for each index I of array a, you can perform the following operation at most once. Choose an arbitrary integer m not equals to ai such that m less than or equals to bi. For each index, you can do this, it seems. Where m not equals to ai and m is between 1 and bi, set ai equals to m. You can do it at most once. If you cannot do any operation, then also it's fine. Let the array after performing all operations be a prime. You can only perform operations in such a way that the following condition holds. For all 1 less than or equals to n less than or less than or equals to n, the G series should be equal. So let the array after performing all the operations, not in the meantime. After performing all, you can only perform the operations in such a way that the following condition holds. After performing everything, this should hold its in. GCD should hold for all of them. You have to determine the maximum number of operations that can be performed while ensuring that the condition remains satisfied. Maximum number of operations. You can at max do n operations, right? You want maximum number of operations. If I see this one, you're given 2 for each index I. You can perform the utmost once. M not equals to ai. This set ai equals to m. Let array. Here time limit is 6 seconds. Here time limit is just 2 seconds. You have to determine the maximum number of operations that can be performed while ensuring the condition remains satisfied. So GCDs of all of them should be equal. It seems that seems something sus, right? GCDs of all. It seems not that easy. Let me think of how AI equals to BI helps here. Okay, BI equals to AI. So this is an easy version. This is supposed to help us solve the difficult version. So M not equals to AI, which is nothing but M less than BI. And set, you can reduce AI. That's what this means. You can reduce AI, and then you want still GCDs to match. L less than R. But you see, GCDs of one big segment equals to, let's just think of this thing. Can you simplify this by telling that? Can you simplify? Is this true? Because GCD of A comma B comma C is equals to greatest common divisor that divides both A comma B and greatest common divisor and so on. So if this is true, all you want is GCD of AI comma AI plus 1 equals to GCD of, you want this, you want just this for all adjacent pairs. If this is satisfied, then everything will be satisfied. Because GCD of three things can be written as GCD of two things and GCD of two things. If this is satisfied, everything else will be satisfied. So you want this to happen, which is for all adjacent pairs, you want this to happen for all adjacent things. So you have to look at two at a time. And you have n minus one such things, okay? Uh, and that GCD should not change, okay? So let's look at A1, A2, A3, okay? Let G1 equals to GCD of A1 comma G2 equals to this, okay? G1 divides A1. We're writing necessary conditions A2. So both G1 divides A2, G2 divides A2. Okay? And this is true even afterwards. So A prime 2 equals to is a multiple of this, you can say. At least it is this big, because even after you do operations, G1 divides that and G2 divides that. But it's all about, can you change it or not? Right? Can you always change everything? See, if all the values are same, you cannot change anything, because changing anything will make it fail. If adjacent values are same, you cannot change those two. Right? Maybe I'll just write that down. If AI equals to AI minus plus 1, you cannot change both. So now you have things where this is not equals to this side, or this is not equals to that side. Can you change all of them? You can also not change. This equals to GI or GI minus 1. Can you change everything else? If you think of that, I think you can likely change everything else. How? These things you cannot change, because yeah, if AI equals to GI or GI minus 1, if AI drops, the GCDs cannot remain, right? Because GCD is less than or equals to AI. If AI changes, if AI drops, it cannot happen. So this, maybe this is the condition. And if this condition is satisfied, then if this condition fails, maybe you can remove all of them. So should I just guess that one? So if its GCD is equal to the next one, it fails. It's just a guess, but I have to prove it immediately. Okay. But we have to prove that. So if it is not equals to GCD of this or GCD of this, that value is less than that, and then you can just move it to its GCD. If you move it to its GCD, then what happens? So this is an even more general guess, but this is a guess. Maybe I have to be more careful. I should not be guessing. Maybe. Damn, it's not difficult. It's somehow it's not that difficult. I'm overcomplicating it. If this thing divides that one, then you cannot remove that. But even if this thing doesn't divide those two, but can you always drop things to GCD? Let's look at the first one. It doesn't have anything this side, right? How is it one here? You take GCD of these two things, it is 67. And if you take LCMs, it is 67. Maybe this guess is right. Maybe this guess is right, but how do you prove that? Should I just submit it for now? What happens if you drop everything to the LCM of that value? I have to prove it, but I'm just submitting it before proving it. See, we got some necessary conditions, but I just submitted it without proving it. We got some necessary conditions. This I got long back, right? I got long back that A2 should be greater than or equals to this one, and then I just submitted that because it's a contest, right? Mm. Now we have to use this one to solve this one. I have to use that to solve C2, okay? But how do I prove C1? How do I prove C1? If I drop everything to that LCM, will it still work? We have to think about that. If you drop everything to that LCM is GCD of these two things, right? And then LCM of these two things, right? So this one became LCM of these three things. So what have we done? What have we done is we have made AI equals to LCM of, yeah. This is what we made. And for such a thing, will gi equals to gcd of ai comma ai plus 1, will gi equals to gcd of, so will this happen? Maybe I minus 1 will go, I minus 1 and I plus 2, maybe they will go useless, and maybe this is actually equal, maybe. Now you have bi, which can be anything, which can be anything. Bi need not be equals to ai here. Bi can be small, bi can be large. See, b of I must be greater than or equals to min. Okay? For you to make it to that. And if b of I is greater than or equals to min, if b of I is less than min, you cannot do that. Maybe this satisfies or what? Yeah, but sometimes here you can do a bit more. Sometimes here you can make non-equal things equal. This need not happen here. See, it should be multiple of min. Okay? It can be ai can be min or min times 2 and so on, but not ai. And if you take adjacent things, If you take adjacent things, their GCD should become equal. Okay, this is already a multiple of their GCD. Okay, this is already a multiple of their GCD. And I'll skip it a bit. I'll go to D. I'll come back later because I haven't proved C1 very clearly. I'm not sure if I can do this C2 very clearly. A bracket sequence is called regular if it is possible to obtain a correct arithmetic expression by inserting plus and 1 into it sequence. For example, this regular bracket sequence. You can perform the following operation on any regular bracket sequence string B. You can perform the following operation on any regular bracket sequence string B. Choose any two disjoint non-empty substrings of B, which are regular bracket sequence, and swap those two substrings. Disjoint non-empty substrings, and then you swap them. Okay. More formally, let M be the length of the B. You can perform the following operations on MB. So if this is that both and swap these substrings, the string will become B1 B up to so on BL1 minus 1 and then BL2 L2 plus 1 up to so on BR2 and then BR1 plus 1 up to so on BL2 minus 1. Okay, yeah, we understood the swapping, right? It will remain regular bracket sequence even after this swapping because you are swapping to regular bracket sequences. On any RBS string B, okay, you're given two strings S and T of length n where n is even such that both S and T are RBS. Okay, this is a good problem, right? They are asking you if they both belong to the same equivalence class or not. Okay, you have an operation that's reversible, which is swap to regular bracket sequences that are disjoint. If it's reversible, then it forms an equivalence class. So you have to now identify what are these equivalence classes here. Okay, you have to now identify what are these equivalence classes. So if you have this and S1, S2, S3 up to so on, all these are same. Okay, so let's hash them. And if you are having S1, S2, S3 up to so on, you can never form a regular bracket sequence from this one to this one, right? You can never form a regular bracket sequence that starts from here and then ends at here because if you start from in between, it will always be deficient. It will always be deficient because it cannot be greater than 0 because still it is greater than or equals to 0. If it cannot be equals to 0, then it has been split. So you can never form those things, okay? You can never swap across S1, S2, and so on. Okay, so sort them and you're done. Hash and sort them. If you finally get same hash, you're done. So this doesn't look that difficult so far, but how do you swap and hash them? So here, what do you do? This is one, two, three things are here. This looks tricky. How is this an S? Oh, you can take these things and then you can replace it with this thing. Okay, that's cool. That's cool. So if you have S1, S2, S3, and S4, all of these are swappable. All of them form semi-equivalence class. So what does this mean? But not empty. Empty is not possible. If empty is possible, I think then if empty is possible, I think then you can just form everything that's possible. Just because empty is not possible, you're having something here in this problem. Okay? If empty is possible, just take this and then keep outside. Just take this and then keep outside. Just because empty is not possible, what all is possible, we have to think. Okay, just because empty is not possible, right? Let's say you have this one. Let's say you have this one. Now, so in this example, this is a pair, and this is a pair, and this is a pair. So you should have one, two pairs, and three empty pairs and one non-empty pair. Okay, take here one, two, three empty pairs and one non-empty pair. Is that it? So number of empty pairs and non-empty pairs is invariant. But is this enough? Can you form anything by just keeping this configuration possible for them? I mean, if I submit this, that might satisfy one, two, three, three empty pairs, one non-empty pair. This might not be enough. So let's look at that one pair. Okay, let's look at that one pair that you have which is non-empty. Right? Either both of them will go or none of them will go. Will swap. And let's look at that pair. We may have like this. All these are pairs, right? And we will have S2, S3, S4, S5 outside. I think with respect to a pair, all of these are invariants, I guess. With respect to a pair, because if it is empty and empty, it will remain empty and empty. If it is empty and non-empty, it will remain empty and non-empty outside. So with respect to a pair, okay, with respect to a pair, whatever these configurations are, they always remain same. But it's not even that complex, I guess. It's just two things. Because you can swap these two things, right, as you like. If there is non-empty on this side also, then you can just move it here. And with respect to this, it might be failing that because you have one thing that is non-empty empty, but you don't have such things here. You have one pair where it is non-empty and empty, but you don't have anything like that here. So is it just this counts? Empty empty, non-empty empty, non-empty empty, non-empty non-empty. I don't think non-empty here and non-empty here is a thing because that can be moved here. This is a guess. Should I just give it a try? But how do I prove this when I have my golden rules telling solutions are simple, proofs are simple, implementations are simple, right? Let's start from from the very beginning, okay? Is this true? Maybe can I use induction of a 4 length? Is this true? For 4 length you have this or you have this. All you can do with this is nothing because you have one empty non-empty. You have one empty non-empty, but you have this one. My initial guess was empty should match and non-empty should match, but the final guess was this. I'm likely complicating this. If you see those partitions, if you have one big thing, you can just drop that. Because why can you drop that? Because they can never be in any subsequence. Okay. Now you have S1, S2, S3, and so on. S5. Now you have to think of these things. Okay. And if you think of these things, you have few empty things. Okay, few non-empty things, and at this level, empty and non-empty must match, and that's it. Count of empty and non-empty must match. Maybe at all levels, count of empty and non-empty should be matching. Okay. Now drop all these things and then look at next level. Let's pass these things to next level, because all of these are now interchangeable, right? And inside them also they are interchangeable, but let's keep that aside. Let's keep the inside interchangeability aside, because even if you pass them to the next level, even there they are inside interchangeable. See, number of non-empty and empty in each level should be same, then it's possible to swap them. Maybe that's the game here. That's being obvious here, right? And once you drop this level now, once you drop this level's pairing, you will do the same thing again. You get what I mean? So you should be able to drop levels and then check empties or non-empties being equal or not. So this is something that I'm guessing again. Be able to drop them and check empties or non-empties being equal. Be able to drop levels and then check non-empty empties or non-empties being equal. Well, I think this is a good enough solution to test it out. But how do you implement this now? How do you form levels? Let's say if you're able to form these pairings, can you form levels? First level would be find the first pairing and then go to the next pairing and then go to the next pairing. That's first level. See number of empties and number of non-empties, that's done. Now the next level would be whatever is in between these things, those things will go to the next level. And when you go to the next level, you have these indices again. You have these intervals again. These are at the next level. And now when you are at this next level next level things, you should split them again based on these things, and then you will have again next new level interviews, and then you can keep going further until you get empty. Yeah, but how do you can you do something better to find these next levels and then the next levels and then the next levels? So you have first level, and then you go down. For each level, I want number of empty things and number of non-empty things. That's it. And then I'll go to the next level. See, I will add and subtract for one string. For one string, I'll just add. For other string, I'll just subtract. So what am I doing here is I'm trying to see, we have this pairs of strings. I'm trying to find its pair, and then I'm passing the insert thing to the next level, and I'm also counting if the insert thing is empty or non-empty. Okay, and then we're trying to go to the next level. We're trying to process one whole substring. Okay, in that we are trying to find the levels, finding the levels in a substring. Okay, uh, we took one thing, we took another thing, we took another thing. Whatever is inside, we pass it to the next level, pass it to the next level. We're counting empty, we're counting non-empty, x plus one or x minus one. Yeah, after this we have everything we want. Now we have to do c of h plus equals to empty, c non-empty equals to this, and then we have to do fun of, yeah, and then what we have to do is, and then what we have to do is, this should be working. Oops, I fucked it up, I guess. My whole solution is wrong now. All of this is wrong. All of this is not needed. Then is it just empty and non-empty? Is that it? There are no levels to that. Is it just empty and non-empty? Maybe then it's just empty and non-empty. I'll just count empties and non-empties. Number of things which have empty inside. Number of things which have non-empty outside. Which are empty outside. I should have solved it better. This was wrong. All of them can go inside. All of these things can go inside. Don't annoy me. I fucked this contest up, I guess. Okay, I hard coded test one, but will this pass for everything? I have a hard coded test one. How I have a hard coded is almost same logic, but what I am applying now is all these things are something. And let's look at non-empty, non-empty, non-empty. At this level, whatever you do, these non-empty things will not inside these pairings they will remain non-empty whatever you do, and outside one if it is empty it will forever remain empty. Outside if the single things or if they are empty, if they will forever remain empty because things can only come from within these things but they can never go outside. So I'm counting this outside if there is something or not, and we are counting number of non-empty things inside plus outside should be equal. Outside will either be 0 or 1, okay? That's always either 0 or 1. And then you have the states number of inside ones. Okay, these two are different. So we'll count outside separately. I have again hard coded things to make it pass, but now let's look at this one. Let's look at, you have some non-empty things, and then outside, is it empty or not? So if this level is something like non-empty, 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 okay, and that's it, then whatever happens, the structure remains same. If you see, whatever happens, things will change, but the structure of number of in the outside level, that will remain same, because whatever, let's think of this one, and let's say, now whatever happens, they may rearrange themselves, but if there's something from inside comes outside, this will always remain outside. Outside will, these things will always remain active. But number of things outside, that can change again. Fuck. See, number of empty pages is an invariant, but then I see this shit. I think anything can be made into this, 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 and so on, and then a series of this. Maybe it's true. Anything can be brought into this format. Think of this one now. Okay, what will I do? I'll swap this with this one. Then I'll, okay, it's already that, it's already in that format. Now think of anything else. Let's try this one. Uh, get the first non-empty one to the start. and then you have empty, empty. If there was something that's something else, you can make that this. So anything can be either gotten into this format or this format in a unique way. Either it will come into this one. If this is dominating, it will come into this. If single ones are dominating, it will come into this. But again, inside this there can be things. Fuck. There cannot be two things inside that. If there are two things inside that, what you will do is you will get that two things out and this will go inside and then you formed more of these things, right? So anything can actually be turned into this or this. think of this one, max prefix should remain constant because you have something, and then what you're doing is you're removing something that is 0, and then you're swapping it with something that is 0, some 0, some 0. And if you see that, anywhere else anywhere else prefix sum will have the same effect. But if you see here, okay, if this has gone, imagine that being here. You got something greater than or equals to 0, you got something 0, you got something greater than or equals to 0, so it will be higher. Nah. So this is number of non-empty pairings versus number of empty pairings. So if number of empty pairings or less than number of non-empty pairings, will be forming this one. So is it really number of empty pairings versus number of non-empty pairings then? How? If there are two groups, you know what you can always do? You can always make the first one like this if it was non-empty, because there are two groups, right? There is something on this side. What you can do, you can get this one and then you can just form this one, and you can keep continuing like that. So remove this I think we have to use that there are two groups, and then you can keep continuing like that, uh, as long as it becomes something like this. Okay, this is true actually now, because let's say it had multiple things like this. Okay, somehow it had multiple things, it is not this. Then you can move these ones outside. Okay, you can move those things outside. This is definitely not this difficult. I'm just not able to solve it. Fuck, 600 solves on D2. It's definitely easier than whatever I'm doing here. It's just number of empties and number of non-empties after you remove the outside things. Is that so? Here you can bring these two outside and then bring that one inside and then bring that one outside and then bring that one outside. So I think this is true. After you remove that, it seems to be true. This was the case that stopped me. But how can you convert this? You can convert this like this. Okay, and then you will just move one inside and then you will bring that back again. So you were able to convert that. So you were able to even convert this by bringing them two outside and then bringing them one outside. You're able to convert that to this. So with this, you can just say it's number of empties and non-empties after you remove the initial ones. Okay. See, I got the idea to check empties and non-empties long, long ago, but I wasn't able to see that. Doing well yesterday just to fuck it up today. What can I change in here and make it accepted? Think quickly. You want GCDs of those LCMs to be LCM multiples they can be, and then you want them to be coprime. See, you know that there are min multiples, and min is already good enough. Okay? So for alternate things, you cannot multiply same prime factor. That's a rule. I should have been careful. I should have been more careful on the. Their LCM is already matching to the GCD. If you add same prime factor to both, that will be fucked.